So Raoult's law is a way of characterizing how much the vapor pressure of a solution is lower than the vapor pressure of a pure solvent. So if we think about a pure solvent, you can imagine that we've got the liquid, it's in equilibrium with its vapor. So if we pump out this space up here and then let the liquid vaporize to fill up that space until we come to equilibrium, and then we measure the vapor, the pressure, that's the vapor pressure, right? Well, we can imagine what's going to happen if instead of doing that, we have another container, and this time we put in some sort of solute. Well, in this case, we know we've just decreased the chemical potential of the liquid, so some of the gas should want to go down into that phase to condense, because it's the liquid at least will have a lower chemical potential. So the gas will condense until a new equilibrium is established with less gas. Okay, so we expect that the P over here is going to be less than the P over here. Okay, all right, so we have to somehow figure out how much less, how much is the vapor pressure lowered by putting that solute into the liquid. And Raoult's law does this by assuming that the solution is ideal. Actually, we have to make two assumptions. We assume that, and we assume that the vapor is an ideal gas. The second assumption is usually a really good one. The top one may or may not be. It's only going to be good if the two components in the solution form an ideal solution. But if we make those two assumptions, we'll see we can get Raoult's law. Now to do this, we actually have to see how the chemical potential of the gas changes when we change the pressure. So we want to remember that the change in chemical potential with pressure at constant temperature is equal to the Mohr volume. So if we write this as a differential, we can say d mu as we go from mu at P1 to P2 is going to be equal to the Mohr volume dP, and we're going to integrate from P1 to P2. And if we integrate this, we get that mu at P2 is equal to mu at P1 plus, well, when we integrate this, we can't assume it's constant, right? We're talking about a gas here, so obviously the volume's going to change when we change the pressure. So we should replace the Mohr volume with nRT over P. That's where the assumption of ideal gas comes from. And when we do that, we can pull the nRT out, and when we do that, we end up with, it's Mohr volume, so we don't need an n there. We pull the RT out, and we end up with this expression, RT, and then it's just going to be the logarithm of P2 over P1. Okay? And normally what we do is we use as a reference the gas at 1 bar. So normally we would say the chemical potential of a gas is equal to, let's just write this as A gas here, is going to be equal to the chemical potential of the gas in its standard state. Remember, standard state for a gas is 1 bar. We'll just write that down here at 1 bar. Plus RT log of the pressure, the partial pressure of A, over the standard pressure. And remember, the standard pressure is 1 bar. Okay? All right, so we're going to use that in our derivation. It tells us how the chemical potential of a gas varies with the partial pressure of that gas. So if we look at these equations, if we look at these two situations, a solution versus a pure liquid, the difference is that we have a lower pressure over here. The vapor pressure is lower. Let's look at that in terms of chemical potentials. Here we can say the chemical potential of a liquid, when it's pure, is equal to the chemical potential of a gas, and actually let's just put those in parentheses. Looks like I'm writing silver there. And this is at PA star. This is not an exponent, okay? This is just a label. Okay, those chemical potentials have to be equal because we're at equilibrium here. Let's go ahead and show that we're at equilibrium. We're at equilibrium over here too. So we could write the chemical potential of A liquid is equal to the chemical potential of A gas at the new vapor pressure PA. Now we're not going to be able to relate these unless we put them in some sort of common language. And the way we're going to do this is relate the gas chemical potentials, the gas phase chemical potentials, to the chemical potential at 1 bar. So let's go ahead and rewrite that on this one first. So we still have on the left-hand side the chemical potential of pure A, but on the right-hand side we're going to relate the chemical potential at the vapor pressure to the chemical potential of the vapor at 1 bar. So we have RT log of the pressure, the pure vapor pressure, which is the pressure that it's actually at, over 1 bar, which is our reference pressure. So this just says the chemical potential of this gas at 1 bar is equal, or the chemical potential is equal to the chemical potential at 1 bar plus this adjustment term that gets us from 1 bar to where we actually are. Let's put a little barrier in here between these two sides here. And let's call this equation 1. Okay. Over here, what we're going to do is say, let's do 2 adjustments. First, let's get rid of this chemical potential of impure stuff by calling it the chemical potential of pure stuff plus RT log of XA. So notice what we just did. We just assumed that the liquid phase is an ideal solution, right? We said it's the pure stuff plus this adjustment term is equal to the chemical potential of the solution. And so we still have the right-hand side is the gas at the new vapor pressure. Well, we can change this into terms of the standard state of a gas, 1 bar. Say chemical potential of A liquid, pure, plus RT log, so we're just going to bring this term down. And then we're going to say this is equal to the chemical potential of the gas at 1 bar plus a term that gets you from 1 bar up to the actual pressure that you are, where you are. Okay? So once we do this, and keep in mind, I think I emphasized this before, that this pressure P naught is 1 bar, right? This is just a standard pressure. Okay? Once we do this, we can say, hey, let's call this equation 2, and then say, what is equation 2 minus equation 1? So what is 2 minus 1? Well, if you do that, you can say, okay, when I subtract, I can see this is going to subtract from that, so that'll cancel. And on the left-hand side, that's just going to leave RT log of XA. On the right-hand side, we say we've got the chemical potential of the gas at 1 bar there, and we have it over there. So when we subtract equation 1 from equation 2, that's going to cancel. So on the right-hand side, what do we have? On the right-hand side, we have RT log of PA star over P naught. We're subtracting equation 1 from equation 2, so we need to put a minus sign there. And we also have the term from down here, which is RT log of PA over P naught. Now at this stage, before we go any further, we should go ahead and just divide both sides by RT to save ourselves the work. Okay? And once we do that, let's go to the next page to write down what we have left over. What we have left over is the log of the mole fraction of A is equal to minus the log of PA star over P naught plus the log of PA over P naught. And we can combine those logarithms, right? We can say this is the log. Since we're subtracting that logarithm from this, we have to divide the arguments. So we have PA over P naught, and then we have, because we're subtracting, we have PA star on the bottom, and we have P naught on the top. We still have the log of the mole fraction over here. And now since we have logs on both sides, we could take the inverse logarithm of that and just get XA is equal to O. And we can cancel these standard state pressures, PA over PA star, or we can just rewrite that as the vapor pressure has to be equal to the standard or the pure vapor pressure times the mole fraction. And that's Raoult's law. And notice that where we got it from making just two assumptions, that the solution that we're talking about is ideal, and that the gas above that solution, the vapor that's forming from that solvent, is an ideal gas. Once we get that, we get Raoult's law. So Raoult's law is a consequence of ideal solution theory. Okay, Raoult's law is a consequence of ideal solution theory. And like all other consequences of ideal solution theory, it's a consequence of the entropy of a solution being higher than the entropy of a solvent. It's purely an entropic effect.